So has anybody got any questions on what we talked about on Tuesday? And we looked at the parts of a hydraulic system. So this is a basic hydraulic system. Uh, Normally, what they don't show on this one though, we usually always have what we call a pressure relief valve on this. And if you've ever dealt with hydraulics, sorry, that would help. Hold on. Hydraulic system would have the tank, a pump, a regulator, control valves, and then some type of actuator out here. So an actuator is anything that takes these pressures and converts it into motion, right? Of course, but once we're through with it, so whichever side, whichever the exhaust side, so it doesn't make any difference to the other one. What we can do with pneumatics, and one advantage of pneumatic, it's a cheaper system to install, and of course it's safer. It's not as efficient as fluids. And another thing that we have to do is we always have to have this return, where we have to actually, once we use the fluid, we have to always bring it back. And of course, in a pneumatic system, if we use gas as the air, which is probably in 99.9% of the pneumatic systems out there, then we don't have to bring it back. We can vent, not unless we're using some other type of gas, and they are out there, guys. But when we're using, especially because of the moisture contents and the pressure we have to put them under, then they might not be using air, because we know what happens when you compress air. It releases all this moisture. So they might be using some other type of gases. Then we talked about compressors, talked about filters, coolers, receivers, which just about everybody calls a tank, but technically it's called a receiver. The receiver on a pneumatic system will also have some type of pressure relief valve on it in case something goes haywire and the compressor don't cut off when it's supposed to, and it builds up too much pressure. We don't want these things to blow up. And of course, another bit of advantage of pneumatics is that we use lower pressures, of course. So what that means, so what's the advantage of high pressure? So what's the big advantage of high pressure over low pressure? Well, technically, no. But I think you got the right idea. The problem is when we come up here and generate a force, that's how much work we can actually do, how much motion we can actually cause. Force is equal to the amount of area you're applying the pressure to times the pressure itself. So what this means is the higher the pressure, the smaller the area that I'm pushing against to do the same amount of work. And I think I told y'all the cylinders on our aircraft that move the big old control surfaces, the ailerons and the elevators and all that other kind of stuff, these things were only about an inch wide, but they was using 3,000 psi pressure. So that means if you're using 3,000 psi up against an area of 1 square inch, you could generate 300 pounds of force with only 1 square inch. Now, if I was going to develop 3,000 pounds of force, and I'm only using, 3,000 pounds of force, and I'm only using 100 psi, that means our actuators would have to be 30 inches just to do the same work. But they're still doing the same work, right? They're still generating the force, but the area so the big advantage of hydraulics over pneumatics is that it's more compact. The actuators themselves can be a lot smaller. The pistons that actually, do the motion and move things around. And then, of course, there are some other advantages, like, of course, you have more control over it because it's considered to be uncompressible, which means you can control the speed precisely. If you had a hydraulic motor, you could control it a lot more precisely. The speed of the the pistons. You can control more precisely. The problem we have with air is it's constantly trying to decompress. So we can't control the speed. We can control the speed, but we can't control it precisely. We can, and it's jerky because every time the cylinder moves, it tries to uncompress or something like that. So that's the big advantage of disadvantage of. So we can't run gases at extremely high pressures because the higher the pressure, it's going to turn into a liquid. So this is the way you buy, you go out and buy these oxygen cylinders or whatever, or these gases for your tank. If you ever bust one of those things up, I mean, it's liquid, but it's underwater, and that's why they have to be so rugged and everything, like these gases that you buy to do your welding with, because they're liquids inside the tank. They turn into gas when it comes out, right? And we let it. So that's the problem we have with gases, is that we can't run them at extremely high pressures because if you do, they will turn into liquids. And then of course, but we don't have to vent it. I mean, we don't have to bring it back to tank. If it's air, we can vent it. And we can use, if you're lower pressures, that means your piping and everything doesn't have to be metal anymore. It's got to be, we can make it plastic. And then also, but your cylinders have to be bigger to do the same amount of work. So, and you can't control it as good. So we looked at this, and we looked at some symbols. By the way, these symbols are exactly the same as if you were in hydraulics. It's just in hydraulics, all the arrows, like these arrows down here, are actually colored in. But basically, it's the same technique, the way we do this. So this is basically, we call it a pneumatic diagram, but it's basically could be a fluid too. But the way they meter it, so fluids, you can meter them either meter in or meter out, but pneumatics, we like to meter out if we can. The only exception to the rule is this guy right here. So if I'm controlling one of these, we don't have the exhaust because the exhaust actually goes out through the cylinder itself. So if we're going to control the speed with this guy, the only option we got is to meter in. So it's going to be a little jerky, right? Yes and no, but notice this guy is working against a what? Yeah, it's working against a spring. So if we're doing a single acting cylinder and we're going to control the speed, then we would meter in. If we're doing a double acting cylinder, then what we would do is we'd meter out. But what we do is we automatically switch between the two with those check valves, right? That's part of the. And it's so popular, guys, that on pneumatic systems, the flow control valves are usually a one-way flow control valves, which means they've got the little check valve in the unit itself. So you probably won't see the actual check valve unless you take fluid power. And I think we talked about. These guys have magnets in them. We talked about rodless. We talked about the directional control valves, how they're generated by the number of positions. So we start off with the number of positions. So this guy, we'd say it's got 3 positions. And then we do it by the number of ports. So this guy's got 4 ports, and we'd say 4. And then they say way. So this would be a 3/4-way valve. Both of these. Now all ours are 2 4-way valves. I think I'd have to look at the Festo lab and see if they've got any in there. Oh no, we have some 5s too. So if they have a 5, what the 5 actually has 2 exhausts, and we talked about that, right? The 5-port valves would have 2 exhausts. Okay. And then we looked at some operators. And this was where we actually looked at what goes on with the valve, and this is what gives people's problems, is they want to look at the valve like it's static, and it's not static. You got to look at the symbol doing what, the whole symbol what, shifted, And so that's what this is right here. So this would be the way it would be drawn on your diagram. But in your mind, you got to see this whole thing do what? Shift. So you don't get this. You can't see this. We got an application called Fluid Sim where you can actually draw it, and when you animate it, it actually shows you the valve shifting, which is pretty cool. But this, I had to do this, by the way, and that was fun trying to get that thing to shift. It's actually two different pictures, two different slides. And of course, this is a picture of a solenoid. And a solenoid is just an electromagnet. So basically, it's got a bunch of coils of wire. And I brought one in. I'll see if the power supply's plugged in. Yeah. Most home units don't have these, but a lot of manufacturers have this, where they actually they deliberately chill the air down, make it condense, and then they separate the water out of it. So you'll see that in a lot of industrial applications. In your house, they usually don't. If you got a compressor at your house, this is one thing they don't have. So it's very, very important if you got a compressor at your house that you keep that tank drained, right, or reservoir. So this is a basic hydraulic system. I think we've already looked at this. And then that's about it for this one. So the next thing that we're actually going to lecture on, so that was just a review, and there was only one slide, and like I said, I messed up on the last one. So we're going to get a little introduction into programmable controllers. Some of y'all that's had PLCs, you'll be ahead on this, and if you hadn't, all we're going to do is look at it from the outside point of view. We're not going to do any programming on it, even though I might, since I've got one connected here, I might pop it up and just show you what would be required to program it. So programmable logic controllers, a lot of people call them programmable controllers. But if you see on a test, what does PLC stand for? If you put programmable controller, you're going to miss it, right? It always surprises me. I'll do that in PLCs, by the way. An industrial computer control system that continuously monitors the state of inputs, makes decisions on those inputs with a customer program. Somebody writes these things to control the state of outputs. So it's just a control system that we looked at already. So we input, right? Then we do what? And then we control. We have our control. And then we output. So we bring in inputs through sensors, through push buttons, through other PLCs, and then the control is going to be a program that somebody wrote, and it's going to make a decision on the state of the inputs. It's going to make a decision on how it generates outputs. The outputs are going to do work. These are going to energize relays. They're going to energize solenoids. They're going to run little motors. They're going to maybe turn on fans. They might turn on lights. They're going to do all kind of stuff. But what gets turned on and what gets turned off is determined by the control right here. So there's 5. So what we do when we write, I'm gonna take this off. When we write programs, we write it in a language. Now, originally, that language was a language we call machine language. When we first got into computers, we literally had some analog computers, and they might still be out there, but predominantly our computers are going to be electrical, and they're going to be what we call binary. So what we do is we write a program in machine language. You would have a big old instruction set, and you'd go up there and it would give you the code. Maybe it might be something like this. And that code, when you look that up, that would come up here, and that might tell the processor to add. And then after that, so the processor's in two phases. It's in what we call the fetch phase or the execute phase, and that's kind of transparent now. But what it does when it goes in the fetch phase, these numbers that come in, it recognizes these as what we call operational codes. Then it switches to what we call the fetch phase. In the fetch phase, whatever it comes in is numbers. So one of them would be a code, and one of them would be a number. So technically, what the processor's doing is constantly switching between fetch, execute, fetch, execute, fetch, execute, fetch, execute. So to do this, it would be almost impossible to memorize all the instructions that are operational codes that the processor would have, unless you wrote programs for years. So what we would do, and we'd have strap in, it had a keyboard that you could enter ones and zeros. You had what we call a key punch operator, where they would come in and they would write their program, and they'd take it to a key punch operator, and they would hit certain keys on the key, and it would punch holes into the cards. Then we'd run it through a card reader and actually download the binary program into the computer. We used to have what we call paper tape, which we would come in, and it had a special typewriter, and when you hit a key, it would come in and it would punch holes into the paper tape. This is the way we used to program CNC machines. We did it with paper tape, which was really neat. And so they had a machine in the machine shop, and they gave us the opportunity to write a program to mill our name in a piece of metal. I used to have mine. I wish I could find it. Then they said, well, this is almost impossible for the average person to understand. So they came out with a language that we called assembly, which you would come in and you would just say add. So that was one of the instructions, add. And then what you'd do is you'd come over here and tell it basically the stuff that you wanted to add together. So these would actually be memory inside the microprocessor. So you still had to understand the microprocessor, or the processor. You still had to understand how it addressed, how to do this, all this kind of stuff. But instead of trying to memorize all these binary codes, now you could come in and you could just type in the instructions. But the problem is this is the only language that the computer understands. So what we would do is we would run it through a binary program. It was a machine language program called an assembler. And then the assembler would convert it into the codes. But it was still a complicated language. It's still considered to be a low-level language because you still had to know everything about your computer. You couldn't say print to the printer because you had to know the address of the port that run the printer. So you had to know everything about your computer, not all the addresses and where everything was at. So you just couldn't do that. So they said, well, we need a better way. So the next high-level language, they had some. They had one called BASIC. Did you ever hear of BASIC? Yeah, BASIC. Beginner's all-purpose symbolic instruction code. This was a high-level language. So if I wanted to get something from a keyboard, I would come up here and I would type in input. And then I would come up here and then I would come over and I would specify a mailbox I wanted to put it in, and we'd just give the mailbox a name. If I wanted something to display on the screen, I would just say print. And then I could come up here and say, like, hello. And this would pop up on my computer screen when we ran the program. This was really neat. It was what we call what we call an interpreted. So we still got to translate it into what code? We still got to get everything into the only language that the processor understands. So we have two methods. After the assembler, they came out with a method that's still used called a translator. And then we have another one that we call a compiler. A translator, what it is it's set up of the actual translator has hundreds of little machine code modules in it. And when you would come up here and you would say input, it would come up here and look at the codes for input, and it would cause the module to run that would cause that to happen. And then when you said print, it would come up here, and this module down here, it would cause the module to run that would cause it to print. So you never actually ended up with a true machine language program because it was translated. Ran real good for us. It gave us the ability to write. I mean, there's no telling how many programs I wrote in BASIC. But it was a high-level language, so I didn't have to learn. I didn't have to worry about the microprocessor anymore. I didn't have to learn where the printer port was. I didn't have to know where the display was. I didn't have to know all that because the translator took care of that for me. But it was translated. It couldn't run extremely fast, so they came up with a method called compiling, where the compiler is a machine language program, and what it does is it takes the program in the high-level language and completely translates it over to the machine language. Of course, it's kind of like the Bible. So the Bible is compiled. So it's originally written in Greek, also some Hebrew. There's several sections. And what have they done? Well, they've took it and somebody compiled it over to your language. And it's your language now. So a compiler actually generates a true machine language program. So this is what we use. So structured text. This is structured text. And what they wanted to do originally when PLCs or programmable controllers came out, they wanted the people that was already in the field of control to be able to program these things. So what we were doing is we were using something called relay logic. And so what we would do is we would come over here and let me find it. I didn't want to go there, but that's okay. So I was going to show y'all a diagram in relay logic. So basically we know a circuit has to have a common. We know it's got to have a power, and we know it's got to have a common. So basically what they did on this is they just came over here. We call this L1 is considered to be power. This is considered to be common. And we just connect our circuits between the two power rails. This became known as ladder diagrams. Because why? Because it looks like a what? It looks like a ladder. And we have individual circuits running between the two rails. And we call the individual circuits, we call them rungs. So when I came up and I said, okay, I want these electricians out there, they understood this. They had been dealing with this for years. By the way, this allowed us to do a lot of automation. We call it relay logic because we could do logic, couldn't do math. But we could definitely do a logic and everything with this. We could do ands, we could do ors, we could do nots, we could do nors. So we could do the 5 basic logic functions that's available in digital. Couldn't do math. If we wanted to count, they had to do it with real neat counters. They would have solenoids in them, and every time something would come by, it would just advance it and cause a clicker to click. So it was actually originally the counters were mechanical devices. So when I came out with a controller that was supposed to control machines, then the logical language for me to use would be this language right here. So we have PLC logic uses what we call ladder diagrams. This is the main programming language that we use in PLCs over here in the United States. But this allows electricians to do this. If we had somebody that came up through computers, or somebody that came up through electronics, or somebody that came up through other types of methods, then they wanted to come back and add other languages so these people wouldn't have to actually learn a language from scratch. So one of the languages they came out, which is still popular, is called structured text. And this is structured text. So if you came up through computer science and you took languages like Pascal and stuff like that, you would jump right into this and program these things without any problem at all. But it's a text-based language. So a lot of people don't understand that. Your really high-level programs are still written in a language like this. It's not in a graphical language. So this is structured text. But you have to learn a lot. You have to learn a lot of syntax. You have to learn the commands. So you have all these different commands that you use. It's just like basic. Syntax is the correct way of writing in a language. In computers, we can live with bad syntax. So I can live with you if you don't put a comma where it's supposed to be, or if you don't capitalize something, or you spell something wrong. Odds are we can read it and we're okay, right? Computers don't like that. Computers, everything, your syntax has to be perfect. If your syntax is not perfect, then it's going to translate it into the wrong machine code, or not even work it at all. So one of the first things we'll learn is syntax errors, but you can still have problems. So you got to learn syntax, you got to run the layouts, you got to learn the commands. So each one of these off-color ones, these are commands. But this is structured text. But if I'd have came up through C, C++, Java, those type of text-based languages, I'd have fell right into this, and I would be able to learn this a lot faster because this is what I'm used to. This is electronics, guys. If you've had digital, then this is digital. Except they use the ISO symbols instead of the symbols that we use over here. So this is an AND operation. So if I wanted this and this and this to go true, it'll generate an output, then this would be perfect for me. So if I came up through digital or through electronics and I didn't want to learn motor controls, then this would be the language that I would choose. Then we have what we call sequential chart. Germans love this. So what you do is you start off with an action, and then what's required to move to the next action. So these little dots right here, these are transitions. So it says, okay, check reactor. If the reactor energy is okay, then I'd move to this one. Charge A completed, move to that one. So this is what we're going to look in here. We're going to translate this over to something that's a little easier to read, and this will be the first lab. Well, not the first lab. This will be the second lab we'll do is we'll set up this troubleshooting chart on this. We'll call it. In fact, we looked at it the other day in one of our lectures. This is basically looks almost just like assembly. This is of all the languages available to PLCs. I've never seen a PLC that supports this language. But this is still one of the ones that's defined by, did I give you all the actual? No, I didn't. It's a double EE standard on programming languages. And I'll tell you where that comes from if you want to look these up. So this is almost very seldom used. We have these guys that you got on your desk, these PLCs only program in ladder because these are older PLCs before these PLCs became international. If we get back into the 315s back there, I know it programs in this language right here. because we programmed in this language when we was over in Germany. And of course, they all program in this language right here. This is ladder. So basically, we run an application. And this is, if you take PLC 1, or Intro to PLC, some of y'all have already had it, I think. This will be the programming language that we'll use. And basically, we just come up here and we can just start a new program. It asks us what PLC are you going to program. Allen Bradley and Siemens puts out a lot of PLCs. And every one of them's a little different. So to tell this guy how to translate it over, you have to select the PLC. By the way, this information is on the PLC itself. So I've got a 1100B. And then this is what I see. And if I want to get something, we call these rungs. And I have to add a new rung. And then I can come up here and bring down the symbol for a normally open contact. And then I can come down here and bring out the symbol for a relay coil. And then we have to understand the PLC. So what we have on the PLC, if you look at yours, is we have all these inputs. And then beside it, it's assigned a number. So we call it an address. So what I have to do is tell my PLC which one of these inputs I want to get information from. So I'll start off and I'll say I for input, and then I'm going to say 0/0. And like I said, this is something that y'all won't have to understand, but we have to tell it how, we have to tell the computer how to select this switch right here. And then I can bring down another one. Can't use it, I want to use the same one here, so I'm going to say :0/1. Oops, 1, Rich. And then I might come over here and put a down drop. I'm going to pull this one into here. Oops. Put this right here. Now, different PLCs address a little differently. Okay. Of course, it's telling me I had a syntax error. Now, why did I have a syntax error? Because there was nothing on the rung. So it's gonna, and this one doesn't automatically clear. So what we do is we just check it. Okay. So 0, 1, 2. So then once I got this written, I would send it to the PLC. Oh, if it's out there, let me make sure it's out there first. It's called a seal-in or a memory circuit. Yeah. I didn't check to see if it found my PLC first. I might have to. Yeah, it's there. So here's the PLC right here. And then so I should be able to. Now when I download it, so what I'm doing right here, when I click on this, I'm just checking it for syntax errors. It doesn't mean it's right, because I might have wanted to use input 5 here, and I used input 0. So, but the compiler does not know. All it's doing is checking to see if you entered these instructions right. And then I'll download it to PLC and then give it a name. This is strange about this application. You actually name it when you save it, when you try to download it. Most PLCs most PLC applications you give it a name when you create the project. And then what's nice about a PLC is that it can actually monitor these inputs for you. So I'm going to come over here and I'm going to energize 0. And without even a meter, I know that this input is being delivered to my PLC because I'm hitting one of my switches. So normally in relay logic, what we'd have to do is we'd have to go out there and get a meter and see if we got power or measure the voltage across the switch or vice versa. Here, the PLC the application tells us exactly if we're getting this, if the PLC is seeing this information. So yeah, this is what we call a seal-in circuit. So this would be start. This would be stop. So stop would be a normally closed push button, and then all I have to do is click it. Now what you have to understand is that my computer does not have to be hooked up to this thing. All we're doing is monitoring the program. I could disconnect this computer and the PLC would still run the program. So once the PLC's got the program, then we don't have to have the computer hooked up anymore. But what I just did is wrote a program in ladder logic, which is a logic or a language that I understand. But my PLC has no idea what ladder logic is. All it knows is ones and zeros. So what happened when I downloaded it to the PLC, it compiled it over to binary, the application that I'm running, compiled it over to binary before it sent it to the PLC. So this is it, guys. This is what's nice about PLCs. So I could have done this circuit in real life, but every one of these would have been true wires. I'd have wires. So all I got to do now is just wire up my inputs and wire up my outputs. We wire every input the same. We don't have to worry about are we going to hook them in series or we're going to hook them in parallel. We wire up all our inputs exactly the same. We wire up all our outputs exactly the same. And then what we do is we tell them how we want the logic in the program, how we want those things connected. So we don't have devices hooked in series. We don't have devices hooked in parallel. All we do is we hook them up exactly the same into the PLC. Okay, guys, y'all take about a 10-minute break. So about 2:10. Come back, and then I'll see if I can get my camera working so I can show you all the PLC. Oh, sorry. Just share the screen, right? Like I said, it would surprise me if you ever ran into this language. So this is what we used to learn for assembly. Then we looked at this. So the advantage of ladder diagrams using relay logic: understood technology, extensively used in older plants, cost efficient for small control circuits. So everything is not going to be a PLC. It always boils down to which is more expensive. So if I can do it with relays and I can do it for a less price, then it's going to be relays. If I can do it with a programmable controller plus relays, you're probably never going to get into a situation where you're not going to have these relays. And the problem we have is the amount of current we can get out of a PLC is not very much. And this is part of the specification on the programmable controllers, it's usually on the magnitude between 1 and 2 amps. But 2 amps would be plenty to bring in a nice size motor starter relay, and then that could run the motor. So PLCs, I've never been into an application where we can never do them with nothing but PLCs. And as we come up here and we look at our manufacturing lines, every one of them has PLCs, every module has PLCs, and every module has relays. Because the PLC is not designed to run or provide a lot of current, but it provides enough current to energize a relay and then let the relay do all your high-powered work. Can be directly control high power and high current. So this is the problem we have with PLCs, is PLCs can't do this. They can't control high power. So they can control low power, low voltage situations, but they can't control high power. But we can definitely take that low power or that low voltage and energize a relay, and then the relay could basically do what? They could go between AC and DC or whatever. So what you doing back here, Kelvin? You playing around with your telephone? I want y'all to put your stuff up. I don't like people not paying attention to me, and then we give tests and you don't do good on it because you don't remember what I do. So disadvantage: requires more physical space to implement than a PLC. Cannot perform complex math, logic, and compare operations. Most modifications require rewiring. So the analogy I use, when they first started when they was manufacturing cars and they was using relay logic, they had two manufacturing lines. One of them was running this year's models, and then then they were wiring the next line to run next year models. Now they don't do that. They have one line that runs the models, and they just change the programs and reprogram the robots every time. So, but like I said, we're looking at which one is more cost effective, right? So, of course, we had to learn a bunch of symbols. So this is the way that this is not the way it appears. This is the way we wire it. So these are relay contacts. This is a solenoid. This is a light. These are push buttons. These are contacts being controlled by it. Now notice what we do is every relay has a name, so they're calling this M1. And then every contact controlled by M1 has the same name. And so they brought this over to PLCs also. RS Logic, the program that I just showed y'all, and we got it running. By the way, if I wanted to change the program, I'd have to take my programming application offline. But what I can do, let's delete this. Yeah. So what I can do is I can come up here, and instead of once I've assigned an address, then I can give this thing a name. And we call it, this one they called it symbols. The new PLCs refer to it as tags. Oop. And by the way, don't check your spelling. We could have done this when I created a program, which is what I should have done. And you can actually do this prior to the program. But now if I wanted to bring a contact into this guy, and I wanted it to be controlled by this coil, instead of me trying to remember this address, then what I can do is I can just come in and I can type it, and then it automatically fills in all this information for me. So in relay logic, if we assign all your outputs names, then it makes sense that they would bring this over to PLCs. So I could come over here now. See, I'm going to check it for errors. Looks okay. I'm going to come up here. I'm going to insert another rung. Now, if I was wiring this up, then it would take quite a while. And if I want to mod, and if I've got a problem, then I have to find the problem in the wiring, right? You understand, on relay logic. If I want to change something, I have to rewire it. Here, most of the time, we can change the control so here, I'm going to assign, so I'm going to come up here and type in run. I've assigned it to this simulated relay right here. And as soon as I do that, it automatically fills in all that information. So what we can do before we even start is we can come over here into this tag, this symbols table, and I can go ahead and I can assign. So I could go ahead over here and I can assign input. So I could go ahead and assign input 0/2. Then I could go ahead and give it a name. No, it didn't work, guys. Oh, I'm sorry, add a record. And then we're going to add an input, :0/0. Not 0, which one I hadn't used? Let's say 4/4. Input, :0/4. And then I can come over here and I can give it a name before I even start. So a lot of times when they write these programs, they go ahead and set up the symbols before they even come in. So now I can come over here and I can just type in play, and then it'll come in and it will fill that information up for me. So what we're saying is that a lot of times before they even write the program, they'll go in and assign all these things names, and then from then on they're programming with a name. Still got an error though, and what's nice, I got a syntax error, but I come down here, it tells me that I'm missing, there's no output operand on there, or output I got. So this is the big advantage of PLCs, but we can modify the program without rewiring. We can, so where was that? So this is a relay panel, a typical relay panel. And then what they've done is I say, we can't take away the relays that do the power, but we can take away the relays that does the logic or the control. So this is what they're saying. All these items here could be replaced by a PLC. So this is technically how the PLC looks. The PLC usually requires less physical space, requires less wiring, can usually be modified without rewiring, can perform complex functions not available with relay logics. So we can't add, we can't subtract, we can't multiply, we can't do trig, we can't do signs, we can't do compares. Well, we can compare two things. We can't do multiple compares. We can't do sequencers. We can't do all this other kind of stuff with relays. We can't do it that way. But we can with a PLC because it's a computer. Requires extensive training to program, requires knowledge of computers, requires external relays to control high voltage and high power devices. So we bring our inputs into an input port. Then it's going to run the logic. Then eventually it's going to generate an output. Some things I think we already talked about syncing, and so we talked about syncing and sourcing in this class, right? Yeah. Syncing uses negative polarity of the DC power supply as a common connection. A syncing PLC port will require a sourcing device. Syncing PLC port input ports are the most common used over here in the USA. So all the PLCs that we have are either configured to sync or they're synced by default. So this PLC that we have on the desk, which y'all at home can't see it, and I can't get my camera to work. This PLC, we establish what we want to be. Oh, let's see, maybe it's come up. No, it ain't gonna work. I might have to restart my computer. Sourcing uses a positive DC power supply as the common connection. A sourcing PLC port will require a syncing device. Sourcing PLC ports are the most common over here in the US. So all the PLCs we have up here either are sourcing by default or we've wired them to source. So technically what we do is we have a common on these inputs, and then we come over here. If we're running syncing, then what we would do is we would come over here and put our negative on our DC source. So hopefully y'all know the short line is the negative polarity. And then what we do is we run the positive down through here. Then what we would do is we'd come over here when we'd connect our device. Let's say it's some type of sensor. We would connect it to one of our input ports. So this sensor right here, it's using a positive as a common. The PLC is using a negative as a common, so the PLC is set up to sync. This sensor has to source. So it's got to be connected up. Its common is going to be positive. Push buttons don't care, but these solid state sensors definitely are going to either be syncing or sourcing. And did we talk about this? So, and this is the designated, if they call it a PNP sensor, these are sourcing sensors. And an NPN sensor is a syncing sensor. And of course, a solid state sensor is going to require 3 wires. And from the wiring, you can't tell if it's syncing or sourcing. Because one is going to be brown. And it's going to connect to the positive. Then 3, no, is that right? We need to look that up, guys. I think the odds are power. I should know that, but you know, sometimes your brain goes dead. So let's go back and look at the schematic real quick, because my brain went dead and I don't want to steer you wrong. Because I think the odds are power and the evens are yeah. So the odds are power and the evens are your signal. Well, is this a syncing sensor or is it a sourcing sensor? It's a solid state sensor. It's got to have both powers hooked up to it. But I don't know. I know this switch right here is sourcing, which probably means all the rest of them are. So if I follow the switch up, I can't write on this. This is not PowerPoint. But if I follow the switch up, here's the plus. It goes over, so it connects to the switch. So all these switches connect to the plus. They don't connect to the minus. So all these are sourcing. But when I see a solid state sensor, if I see a diagram of a solid state sensor, all I know is it's got to be powered up. So 1 goes back to plus and 3 goes to minus. But which one is it switching? Is it switching the minus out to 4 or is it switching the plus out to 4? Just looking at the symbol does not tell you if it's sourcing or syncing. Now I know our PLCs are using syncing inputs, so I know these are all PNP sensors. They're all sourcing sensors. I know that. But you can't go by the symbol. So you come up here and say, okay, I need a 1B1. It's made by this company, and I call them up. And if you don't know the part number and you order a NPN sensor and it's supposed to be a PNP, then you got problems. So we are putting together some boxes. They're over there in the other lab. I need to bring them over here, where we're going to actually let one class wire the PLC. But the problem is the PLCs are set up for syncing, and the person that bought the inductive sensors bought syncing sensors. Somebody gonna say something? So you got a syncing sensor hooked up to a syncing input. So what's going to happen? But it wires up the same. 1, 3, 4. It's just that what it's going to do is switching So what a sinking sensor would do is, I'll have to bring up a PowerPoint. Yeah, somebody needs to mute. And this would be 4. But the other sensor, so this would be an NPN sensor. The other one I still wired up exactly the same, except what it does, it comes over here and switches this one to the output. So and this is still labeled what? 4. So it's up to you guys when you have a sensor that's bad that you make sure you do what? Buy the right one. So an inductive sensor is an inductive sensor. If it mounts on your mount, then you don't have to get it from the same company because the wiring is the same. But you can't go out and buy what? So on ours, we need to make sure they're what? We need to make sure they're PNP sensors. Because what it's doing, it's electronically switching the plus out. And so what happens, if I came over and used this one, this guy is using minus as its common. This guy's using minus as its common. We have no current flow, so it appears that the sensor's bad. So you go out and say, well, I need an inductive sensor, and you go into your stock room and you find one and say, well, this is about the same. I'm going to go out there and hook it up, and you hook it up and dang thing don't work. And you say, well, this must be bad too. Then you go back and do another one. It's bad. I've seen people go through like 3 sensors and they think they're all bad. But they what? Yeah, they just picked the wrong one. They just went back there and picked one. They knew it was an inductive sensor, but they picked the wrong one. So this is, and it's in the part number. I mean, it's not in the part number, it's just a part number. You know, if you just call the company that makes it and you say, I need an inductive sensor, and they say, well, you need a PNP or NPN, and you say, well, I guess I get a NPN. And then you hook it up and it don't work, you know. And you pulled it out of the box, you paid $60 for it, you pulled it out of the box, and now the company won't take it back because you already mounted it. So on these solid state sensors, you can't tell from the symbol whether it's sinking or sourcing because they all wire the same. And some of them have a 2. So they'll have a 2 coming out. And these are going to be these guys like this. So they're going to be these. So they're going to have a normally closed and a normally open, but it's still going to be sourcing or sinking. So a 4-wire sensor, and what's the colors? That's going to be on that. It's going to be on the next test, right? Okay. 1 is what? So plus is what? Brown. Good. Minus is blue. Good. Somebody got it on. 4 is? 4 is? And if we had a 2, then it would be white. So white would be the normally closed and black would be the normally open. So you got a single pole double throw switch in a 4-wire sensor. We do have some over. None of ours, I don't think, are 4-wire sensors. I can't think of any that's 4-wire sensors. But there is a couple that if we take sensors, they're not wired up, but you can actually see the white wire where it's actually single pole double throw. So this is the S7 314C PLCs. It has 24 syncing inputs. It has 16 sourcing outputs. It's got analog and digital. I've never figured out what this resistance thing was. I've never seen that before. It uses it provides what we call 4 to 20 milliamp current loop. What this means is we have problems trying to send voltage over distance. The problem we have, and these are high impedance circuits, which means these inputs pull almost no current at all. So the PLC pulls current. The outputs is where all your current is. So what happens is if the higher the impedance or resistance of the circuit, the more likelihood for electromagnetic interference to interfere with your voltage. So EMI can change voltage if there's hardly no current involved. And sometimes y'all can actually hear it. Y'all can hear your TV start hissing at you. You know, light, huh? Street lights, yeah. When you drive your car in there, sometimes you pick stuff up on your radio. Well, that's the problem we have with electromagnetic interference. Uh, electromagnetic interference, cannot generate a current. It can change a voltage, but it can't change a current. So one of the most popular in industry is what we call a 4 to 20 milliamp current loop, which means if you're outputting an off, there's never an off. So an off would be equal to 4 milliamps of current flow, and then a true or a on would be equal to 20 milliamps. So we can run these over great distances. We had a 4 to 20 milliamp current loop over there before they moved. Montclair Hospital used to be over there where East Lake Mall used to be. Now it's Grandview. They moved it over to 280. Used to be Montclair, and it was a huge hospital. So we ran one, good gracious. It must have been a half a mile. We run a current loop that far. Couldn't have did a voltage, but a current loop that far. But they're very reliable, so you're going to run into these if you're in a company that has a lot of EMI in there, a lot of motors and stuff that run all the time, because they're almost immune to electromagnetic interference. So this guy's got 4 to 20 milliamp current loops inputs. These are inputs. It's got 2 4 to 0 to 10 volt analog inputs. Then it's got a resistance input. I don't know. The analog outputs, it's got an analog 0 to 10 and 0 to 5. All these inputs right here are 24 volt, by the way. So this is what's on the Amiltor line. We don't have any additional modules on it. So it's what I refer to as a hybrid PLC, which means it comes with a bunch of fixed ports, but you can come over here and you can snap the cover off the side, and you can buy modules and snap them in here to get additional ports. It uses a we used to call it an RS-232 connection. I'll have to show y'all. Y'all remind me to show me all the people that's virtual when y'all come in on Tuesday. It's what we call a DB9 connector, and the way it's set up is the female has a metal shell around it. It's up on a plateau, and then the male comes over. It's got a metal shell that fits over the outside, and it's in the shape of a D, so you can't hook this sucker in backwards. This is what we don't like to say things are Murphy proof, but this guy's about as Murphy proof as you can get without cutting the shell off. And then we network them by using what we call a daisy chain, and we might get into a little networking in here. I don't know, depends on what we have. So we put a connector on here. And then in the other class, y'all saw this. It has another connector that mounts on top of this, and then it daisy chains down to the next module, down to the next PLC, and the next PLC. So it's what they call a bus topology, but it's a daisy chain topology, where we can actually network the PLCs together. A blockchain. Oh, you mean did you pull? I don't. Oh, okay. Yeah, well, another way they used to do it when they first came out with the bus topology is we would have a T, and then what we would do is we'd run one cable the entire length of the network, and then each T would drop down and come down into a computer or a node. This is the first way we network, guys. Before what we call the star topology came out. The Festo, the S7s are actually using a what we call a star topology, and we'll show you all that. The topology is the way you connect networks together, so to share information. This is what's on the Festo line. It's using a MicroLogic 1500. And what's neat about this is that it's got its own DC commons. Every group's got its own DC commons. So we have the first group, which they call group 0. And then we have group 1. Yeah, here's group 1. Oh, I'm sorry, here's group 1. Here's group 1. And then here's group 2. And each one of them's got a common. So what we could do on this one is I could come over here and hook the minus up to this one, and these would be syncing. I could come over here and use and hook the positive. I could hook up the positive to this common, and it would be sourcing. So on this PLC, you can set them up. And the ones I can't get my camera to work in, but I'll show you the other class. This is the way this PLC is. If you look at the top, it's got 2 commons on it. I think one of them is a common for 1 through 4, and the other one's a common for 5 through 6 or something like that. And those 2 wires that go in there are both negative. So this is set up for syncing inputs. But I have the ability on this PLC to configure it which way I want it to be. This guy I don't. This guy was bought with syncing inputs, and it was bought with sourcing outputs. This guy, I can come up and I can, in groups, I can make this group sync, I can make this source, I can make this sync, but I have to do them in groups. The output is what we call a relay output. So with a relay output, so we see right here it says volts AC, volts DC AC, volts DC AC. What it means on this one is since it's got a relay, then we can make these AC. By the way, syncing and sourcing only applies to DC because AC technically has no polarity. So we could hook AC on those things, and we could have AC outputs. Over here I could hook the plus, and this would be a syncing output, a sourcing output. Over here I could hook the minus, and it would be a syncing output. Now you can see it, like I said, y'all remind me Tuesday, and I'll show you that. But on the bottom, you can actually see where I've run the red wires down there. So this is set up to run sourcing. But it has a common for every output. So we're showing them the little 1100s. Also, the Allen Bradley has got a secondary module connected to the right hand side. So this is what's on the Festo. We've got all the programs for this. So if you take PLC 3, which we call PLCs and automated systems, what you will do is you will take the programs that's written for the Allen Bradley and you'll convert them over to Siemens programs. And you'll also be able to get a Siemens PLC certification in that class. So that's basically it on the PLCs. You know, we looked at a little programming, and what I wanted to show y'all is once you learn how to program these things, it's not that complicated. And what we're doing is we could do the same thing with relays, but I would have to run all those wires. And what's nice here is that when you hook up inputs, all your inputs hook up exactly the same. So I would come over here and I would have a common. And then I would come over here, and of course we're running syncing inputs. And then I would come over here and I would put my input devices, and then I would hook up each one of my input devices to one of my input pins. And they all wire the same. But in my PLC, let's just say these are inputs. These are push buttons, and this is input 1. And this is, let's say, 0, 1, 2, 3. Well, in my PLC program, I could come over and I can say 1 in series with 2, in series with 3, in parallel with 5. And then I could come over here. It don't make any difference. So your inputs and your outputs are not hooked in series. They're not hooked in parallel. They're just hooked one to each input port. And then it's in the program where you decide, are they in series or are they in parallel? So I've seen people do this, and then they'll try to come over here on their input, and they'll try to come over here and do this on their input, and they come into the input of their PLC. But that's not the way it goes. What you do is you take one input, is hooked up to each port, And then when you write your program, you say, okay, when that program is pressed, this and this and this has to be pressed or stuff like that. So we don't have series circuits. All we got is just outputs hooked to outputs, one output per output port, one input hooked up to each input bit. And then it's the program that determines how the logic, how we're going to put this together. So does everybody in here, you hadn't had PLCs, have you, Jalen? Yeah. I know Kelvin, you hadn't? So so this is it on PLCs. So what we'll do, so we're fixing to let group, the Tuesday group is going to bow out. I think I got all y'all on roll. And then we're going to let the Thursday group tear the line back apart. I put it back together, by the way. And so they'll tear the line apart, and then we'll let them try to start on the next lab. Okay, y'all got any questions? So this was just an introduction to PLCs. From your point of view, syncing, sourcing is very, very important. Knowing how to run the application so your PLC can troubleshoot for you. Also, another thing we need to understand is the PLC has indicators on the front of it. So the PLC has all these light emitting diodes out here that it will show you when an input gets to the PLC. So if the light's on, you know, ours is running off 24 volts. So if the light on an input is on, the LED is on, you know that 24 volts is getting to the PLC. So what you just did is you checked all the wiring from the sensor to the PLC without pulling out an emitter. If you go out there and somebody triggers the sensor and the light doesn't change, then either the sensor's bad or you got a bad wire coming from the sensor. When an output goes true, it's going to come on. So an output has an LEZ too, so you'll have to identify those. So if you tell it to generate an output, then that LED would come on. That would tell you that it switched 24 volts to the output. And then the relay doesn't come in. Well, on that, you might have to pull out a meter, right? You understand, and verify that the 24 volts is getting there. If the 24 volts is not getting to the relay, then there's a broke wire between the PLC. If the 24 volts is getting to the coil of the relay, then that would mean what? That the relay is bad. And relays go bad, guys. They got a bunch of coils of wire in there, you know, and they can't take any consideration in all it. And shocker, and the wiring is so thin on the relays because it's using what they call magnetic wires. It doesn't take much chafing to cause those things to go out on. So, any questions from the virtual crew? So when y'all come in Tuesday, we'll come back and let y'all, and hopefully I got my camera working by then too, my external camera, and we'll see if we can look at these PLCs a little better. I'm going to take this group back and let them look at the PLCs, how to wire them, and not basically wire, but how they are wired. And we'll do that when your group, Tuesday group, when y'all come in on Tuesday. All right? All right, y'all be careful. Y'all be safe.